Okay. Alrighty, let's go ahead and get started today. And we're going to continue off by continuing with talking about mixtures of gases. So, we saw yesterday, I kind of gave you the example where we had, 3 containers of same volume or whatever. We had some blue gas molecules and some purple ones. Or were they green? I don't know, but it doesn't matter. Alright. And we saw that the pressure of the blue one and the pressure of the purple one, whatever, I'm using 1 and 2, but A and B, whatever, doesn't matter. The pressure here one second. Off to an exciting start, aren't we? Are you gonna be naughty like that, mister? Come here, sit on my lap, okay? One of them is defending a food bowl that is like completely empty. I don't understand. Like there's nothing in it, and they're all fighting over it. It's like, okay. So it was the total pressure, of course, would be equal to the ones made by the blue gas and the ones by the purple gas. So that's going to be kind of how we're going to look at mixtures. And since we know that pressure is proportional to moles, we're going to look at that idea of the mole fraction again. But suffice it to say, what we've kind of used so far, although we've only been dealing with single gases, is that technically our ideal gas law should look like this. This is kind of what we've been doing so far. And it works, no problem. And it will continue to work. So if you have a total pressure, you can find out your total moles using the ideal gas law. But you can also just look at one particular gas in a mixture. So let's just say that. So all gases in the mix, or you can look at one gas in particular. So that means that if you can figure out the partial pressure, just the pressure of gas A, whatever that happens to be, you can calculate just moles of A. Whatever A happens to be. Again, it could be xenon, methane, who cares? Caffeine. If you sublime caffeine, it does exist as a gas. It's pretty cool. Anyways, so we can kind of do cool stuff with these things. But first, let's kind of work on that partial pressure idea before we jump into kind of revisiting the ideal gas law. So, we kind of just looked at yesterday that we had this idea of what's called a mole fraction. And so for whatever your substance A happens to be, we did it for air yesterday, but we can do it for something else. So let's say we have one mole of helium, 3 moles of xenon and 2 moles of, I don't know, how about chlorine in a container. Oops. Container with a total pressure of, what shall we say? We'll make these numbers easy. How about 12 atmospheres? We can see what the partial pressure of each gas is. Can you guys hear that he's like licking my hand pretty aggressively? And then there's the creature. Because if that's distracting, I can move him away. But we'll see. Okay, you can hear it. Okay. Okay, Oz, let's go over here, buddy. Where should we put you? Okay, he looks like he's done guarding the thing, so maybe there will not be any more explosions. I don't want anybody to be distracted, so... Okay. So, we have this mixture of gases, and we have a total pressure. And we're just looking for the partial pressure of each gas. And so we remember that the partial pressure of gas A, whatever it is equal to the mole fraction times the total pressure. And so for all of these, we just have the moles. And so what we're going to want to do is figure out what the mole fraction is. Did I write mole fraction? I did not. Okay. Mole fraction. That's this stuff. Okay. So, if we're looking at, let's say, helium, well, that would be equal to the mole fraction of helium times the total pressure. If we look at the mole fraction of helium, that's the moles of helium over the total moles. And so there are 6 total moles here, right? If we add them up, we have 1, 3, and 2. Add those up together, that would be 6 moles. And so we're going to see that the mole fraction for this will be, what, 0.16 or something? If you do the calculation, 1/6. And so the partial pressure of helium will be 1/6, or 0.167, whatever you have, times 12 atmospheres. And as a result, we end up getting 12. So then we get 2 atmospheres at the end here. Technically, this is 3 sig figs for the 1 and the 6, but I was being lazy. There, we'll fix that. Since these are nice, easy numbers, I kept it as a fraction because it's easy to do the math that way, but very often you'll end up with a decimal number that's not an easy fraction, so you'll probably just want to carry out. You know what, let's just do that. Okay. Notice mole fraction doesn't have any units, because moles will cancel out with moles, so we don't have to worry about those. So we can say that the helium exerts a pressure of 2 atmospheres in this container. And if we do the same thing for, what else did we have in here? Xenon, okay. We'll be a little bit quick this time. The mole fraction of xenon will be just 0.5, technically with 3 sig figs, so we should keep that. And so doing this, we get 6 atmospheres. And without even having to do it, we can see the pressure of, what was it, chlorine, should be equal to 4 atmospheres. We can do that because we remember that the total pressure is the sum of all the partial pressures. So we know within the helium and xenon we have 8 atmospheres. We know we have 12 altogether. So that's how I was able to calculate that. So this was the total. This was helium and this was xenon. Of course, you could do it with the mole fraction thing. Slightly more work, but it'll get you the answer just fine. No problems there. So that's kind of how we can look at things like this. Alrighty, any questions on this partial pressure stuff? Before we move on to doing it in an example. Alrighty. In that case, let's go ahead. Let's see this in action. So, let's take a mixture of let's do 3 gases, I think. Let's say it's going to be 40%. Methane. 22% nitrogen. And the rest, let's see, how about water vapor? Exciting stuff. The temperature is, let's see, it's going to have to be above 100, so let's make it 400 Kelvin. And the pressure is 2,000 millimeters of mercury in a 16-liter container. Okay, there we go. These problems always take so much time to write out, you know, because there's so much information in them. Okay, what is the mass of each gas in the container? So just to note, whenever you see percentages with gas mixtures like this, that's the same as the mole fraction. So it's telling us already that we have 0.4 as our mole fraction for methane, 0.22 for nitrogen, and then we have to figure out what water is going to be, which I guess will be, what, 0.38? Something like that. So just keep that in mind. So one thing that I've noticed through teaching this course for so many years now is students tend to just see percents and they're like, okay, empirical formula. Let's divide by molar mass, get moles, and something, you know, turn these into grams or something. It doesn't work that way with gases. That works for empirical formulas only. That's something that we're not going to see again until the final exam. So don't be just converting these percentages to grams. Okay, it does not work like that. For these, that percent is a mole fraction. Okay? So we can kind of do this 3 ways. Rather 2 ways. One of them involves 3 parts, though. So we have option 1 is to use the temperature, volume, and total pressure to find the total moles. And then from that, use the mole fraction to calculate each moles, which I would recommend. I think this way is faster. Alternatively, if you were so inclined, you could do the green method, which is use mole fraction to find what are these, methane, and then use I can keep that Na. Then you can do the ideal gas law 3 times. Which is fine. Either way will work. You kind of have two pathways here. I think the purple way is more efficient because the calculations are easier. We only deal with the ideal gas law once, and then the rest is just basically multiplying by those mole fractions, and that's it. However, if you were so inclined, you could totally find the partial pressure of each gas first, and then use those partial pressures to figure out the moles. Oh my goodness, I should have solved this for moles. Oh well. Doesn't matter. So let's do it the top way, if that's okay with everybody. I think that would be the easiest way to do this. And in that case, we saw that the temperature was, what, 400 Kelvin? The volume was 16 liters. And the pressure total was 2,000 millimeters of mercury. Right? If I remember correctly from the question I just came up with. Yeah. Okay, cool. So with that in mind, we can figure out what the total moles is in this particular container. But we see that we have one unit that's not allowed. So we're going to have to go ahead and fix that unit first. So remember the conversion factor for this is 760. We are going to ignore sig figs for the 760, so we'll just keep our 4 sig figs here. And we get whatever we get. Let's see what that's going to be. 2,000 divided by 760 is 2.632, we'll say. Actually, it is 4 sig figs, so we will not round yet. Okay. Okay. So we have our pressure now in atmospheres. So we know that N equals PV over RT. And so we can plug all this fun stuff in. We have our volume of 16 liters. We have R. And then we have our temperature. So doing all this stuff, we get the total moles is going to be, let's see, so that number times 16 divided by 0.08206 divided by 400. All right, we get our total moles is 1.28. And we'll just kind of keep the, I guess it'll actually be a 3 for just rounding errors. Let's kind of minimize those. And so now we know, for example, the X for methane, wow, was 0.4. And remember that that means X was equal to individual moles over the total moles, right? So that means that individual moles of A, whatever we're looking at, is X of A times N total. Just like the partial pressure is mole fraction times the total pressure, it's exactly the same here. So we can find out that the moles of methane is 0.4 times 1.28. Let's see what that is. Multiply that by 0.4. We get 0.513 moles of methane. And since the question did ask for mass, we're going to go ahead and have to do that conversion too. So do you see all the fun stuff I can do with gas laws, just throwing the same equation at you, and you have to do all these extra calculations? Unit conversion after unit conversion after unit conversion. Okay, so let's take that number. And let's see, that's going to be what, about 16.0, I don't know, 4 or so grams for its molar mass. Carbon plus 4 hydrogens, 12 plus 4, yeah. So, okay, and doing that, let's go ahead and do that out. 16.04. We get 8.23 grams of methane. So hooray, we have our first answer. Any questions on the methane one before we do the other two? How interesting. I see I do get the blue things here as well, depending on the angle. So this way is more blue, this way is less blue. Very curious. Alrighty then, if there are no questions on that, let's go ahead and take a look at the other two gases. So we had, I don't even remember, 22 for nitrogen. And so therefore the moles of nitrogen would be 0.22 times 1.283. That's the total moles that we calculated using the ideal gas law. And let's go ahead and get that back here. Okay, and so if we take that number and multiply it by 0.22, we get that we have 0.2822 moles of nitrogen. We're going to use our molar mass of nitrogen. Remember, 2 nitrogens because nitrogen is diatomic. We do this 28.02. 7.91 grams nitrogen. And then the last one, the water, we haven't figured it out. So we need to do 1 minus 0.4 minus, I guess I should put the sig figs in, minus 0.2. So the water will be 0.38. It's just everything that's left, right? 100 minus 40% minus 22% is 38%. I hope. Yeah, that should be right. And so that'll be the mole fraction for water. So just like before, now we do 0.38 times 1.283. Okay, so multiply that by 0.38. And we get 0.4874 moles of water. And if we take that and convert it to grams, water's molar mass, of course, 18.02. Something we've calculated many times now. Oops. And from that we get 8.78 grams of water. Hooray. So notice these gram quantities are actually all pretty similar to each other. They're all right around 8, right? Thereabouts. And so if we were to look at the original problem, I'm going to just scroll up for just a second here. If you were to look at these numbers, you know, there's not really an easy way to go from 40% to 8 grams, or 22% to 8 grams, or 38% to 8 grams. Like, these ones, unfortunately, there's not really an easy way to get through these. So it's just having to calculate it all out. So this is what we will end up with. If you did end up going the other route, that's just fine. You would just have to do the ideal gas law 3 times. And then you should get the same answers. So just more math, I suppose. Because this math is just multiplying after the fact, rather than having to use R and T again and all that stuff. So a little bit easier this way, I think. Alrighty, any questions? Another way I could ask, so I'm just thinking out loud, like what other things I could ask you with this sort of fun business, is I could say, like which of these gases has the most mass in the container. And so if that was the question, like which gas is the largest by mass, it would be water in this case, because 8.78 will be the biggest one. If I were to ask you, which gas was the biggest by moles, well, that would be methane, right? Because methane was 40% of everything. So, it's just kind of small little bits here and there I could ask you. So, with this, I do have some homework for you guys. For once, it will not be a worksheet. It's actually homework questions I've written. And so you'll be able to work on something similar with this one. All right. So, any questions on other gas stuff? I'm just going to take a look at our syllabus here. What class are we? 101? Yes. I want to see kind of like where we are in terms of exams coming up and all that business. I think we're still going to cover solutions before our next exam, but I just want to make sure that that exam is not next week. So let me just check that real quick. But in the meantime, yeah, throw out questions if you have any. I did get a question on Discord. Like I woke up and read it and then forgot about it. But we will definitely do a review before the next exam. So don't worry about that. And so we'll definitely have that on a Thursday before our exam. So let's go ahead and see what that is. So it looks like your exam is going to be right before spring break. So it is scheduled for next week. I think what we'll do, instead of starting chemical reactions next week, we can just do that the week after. Let's push exam 3 Shall we have exam 3 maybe at the end of next week, before spring break? Would that work for everyone? I'll put a poll out. We'll see if that works for everyone. Maybe we'll just try and make it work that way. And if we decide to make it maybe I'll give you both days on the weekend to do it or something. So maybe Saturday and Sunday that weekend to do it before spring break. Maybe that'll be the easiest. We'll see. So again, we'll push the exam, so it's not going to be Monday. We'll just go ahead and can start with solutions now, and we'll continue it through next week. Maybe we'll have an extra day to review, because this schedule was a little bit more, what's the word? I gave a lot of extra time at the end of the semester with the schedule I put up here. So we'll be fine if we push things a little bit. So let's do that then. So we'll just push the exam a little bit. I'll give you guys some options. We'll make a vote and we'll see what you guys want to do. And we'll have that taken care of. Okay, well, in that case, let's go ahead and talk about solutions. So solutions are going to be homogeneous mixtures. If you remember what homogeneous meant, it meant that it's going to be the same throughout the mixture. So whatever kind of sample you're looking at within a given mixture, everything should be the same. So salt water would be a solution because the amount of salt is evenly spread out throughout all the water. Air is a homogeneous mixture. It's going to be, the same proportions of nitrogen, oxygen, argon, wherever I am in the room. That would be pretty sucky for our lungs otherwise, right? They'd have to be like, I wonder how much oxygen I'm going to get if I go to that side of the room. You know, that would be pretty awful. So definitely homogeneous mixtures are worthy of studying. So speaking of which, we have a couple of common solutions. You know, air is a very common homogeneous mixture, but there are other ones that we may not think as obviously would be solutions, like steel, for example. Steel is a solution. Brass is a solution. Bronze is a solution. Vodka is a solution. Salt water. Honey. Let's see. What other ones? What are good solution examples? Now that's a colloid. I mean, we have so many. Ketchup. Except when it separates, right? You know, if you haven't opened it in a while, you get that like watery layer on the top. Peanut butter. You know, we have tons of various solutions that we deal with all the time. And so we're going to see that they can take all sorts of different forms. So note, for example, they can be solids, liquids, or gases. So air, of course, being a gas. Something like steel would be a solid. And something like honey would be a liquid, right? So we can see that solutions can be any state of matter, although we typically think of solutions as being liquids, right? You know, if you go into, you know, Shutterstock or whatever, and you just like Google chemistry, you're going to see all these colorful beakers and things like that filled with colorful liquids. And so, you know, very often we do deal with liquids as solutions, but technically they can be any three. All right, and so we have some vocabulary associated with these. Solutions are made up of what are called solutes, which are going to be the things that are dissolves. They are dissolved, rather. But that's not really a formal definition. Typically, we refer to solutes as the non-major component of the solution. This abbreviation, SOL''N, is commonly used for solution. I'll write that out just to make sure that we have that, but I'll be using that abbreviation probably a lot. So those are going to be the non-major components. So by major, we just mean majority. Whatever the majority of your solution is, whatever the non-majority is, the minority will be the solute. You can have as many solutes as you want. In fact, many solutions have hundreds of solutes. And so that's totally, you know, pretty common. So if you look at, you know, if you were to take a cell and blend it up, you would have thousands of different solutes in there. However, we can only have one, what is called the solvent, and that is always the major component. And it does the dissolving. And so we're going to see that very often for us. We'll see that water is a solvent that we use. Actually, I'm not even going to say a solvent. We say it's the solvent. You can only have one. You can only have one solvent in a solution, and it's always the major component. Ideally, that means whichever one has the largest mole fraction. So typically, because water is such a small molecule, has a very low molar mass, it's very often going to be the solvent. You can only have one solvent. You can have hundreds of solutes if you want. You could have one solute. Doesn't matter. You have to have at least one solute and only one solvent. So if we want to think about some Actually, one more thing. The solution often takes the state of matter of the solvent. So if you're at all, confused, very often your whatever you see as your solution, your whatever state of matter it happens to be, is likely the very same state of matter that your solvent would be at room temp or at whatever temperature you're looking at. So if we, for example, look at something like salt water, of course we have the solute, which would be salt, and the solvent would be water. We have one solute, one solvent. The solute is the stuff that is being dissolved. The solvent is doing the dissolving. If we think about salt water, it looks like water, right? It is a liquid. It flows. It's clear. We're going to see again very often the properties of your solution will be more similar to that of your solvent than to your solute or solutes. If you want to think about plasma, like blood plasma, we have a lot of solutes there. We have sodium, we have chloride, we have potassium, we have a little bit of calcium, we have albumin, and hundreds of other proteins, all dissolved in one solvent, which is water. I mean, we also have bicarbonate in there. We have phosphate. So we have tons of various different things happening in our plasma, right? Hundreds of proteins in there. You've got proteins carrying molecules. You've got fats. You've got cholesterol. You've got your like LDLs, your low density lipoproteins. You've got all sorts of different things going on in your blood plasma. It's a very complex solution. But again, one solvent, and that solvent is water. So you can see you can have as many solvents as you want. Solutes as you want. One solvent. If we look at something like steel, steel is a mixture of iron and carbon, potentially with other metals put in, nickel, chromium, all sorts of other bits in there. But if you think about steel, what does steel look like of all those things? If we're just thinking of iron and carbon when we deal with steel, carbon is charcoal. It's black, it's powdery, brittle, whereas iron is silvery, hard, bendable, all those things. We're going to see that, of course, steel is more similar to iron, right? They're both metals, or metallic, as it were. We're going to see that the solute are going to be carbon, potentially nickel, chromium. I'm not quite as proficient in metallurgy as I would like, but my understanding is that nickel and chromium are kind of the biggest two other additives to steel, just to help resist corrosion or to give it particular properties. And your solvent for this would be iron. Let's make that a little bit prettier. Does anybody know if there are other metals commonly used in steel? I don't know. I've been watching Forged in Fire a lot recently, and I'm very enthralled by the process. So it'd be just cool to know. And of course, if you vary these, amounts of carbon or nickel or chromium or whatever, you end up with different properties for your solution. It's the same if you were to vary the salt concentration in your salt water. You could make it where it is still drinkable, or it could be completely like poisonous to drink. And so, just varying your ratio of solute to solvent, you can mess with the properties as well. All right, any others we want to go over? I don't know. Let's do one more maybe. What shall we do? How about we do vodka? Vodka, of course, is a mixture of ethanol and water. And we see that often vodka you see would be something reported as 40% ethanol by volume. And so while that technically is not a mole fraction, it is a volume, water is going to be, because again, the water is so much, without having to calculate it, ethanol is fairly less dense than water, but ethanol is a much larger molecule in terms of molar mass than water is. So you can fit a lot more water molecules into the same amount of water than ethanol molecules. So you will see that water will still be your solvent here. You can just trust me. We'll do that calculation later, don't worry. That's always a fun one, to calculate the freezing point of vodka. So you can see why it doesn't freeze in your freezer. That's something we'll probably hit next week, though. The solvent, of course, will be water, just like before. Oh, let's do another one. We haven't done a gas solution yet. Remember that air is going to be 78% nitrogen. So nitrogen gas will be our solvent. Our solutes would be carbon dioxide, water, oxygen, argon, xenon, helium, whatever, all these other gases we have hanging out there, methane, sulfur dioxide, whatever our particular air sample happens to have in it. And so we're going to see that our solvent will be nitrogen. All those other components are solutes. All right. Cool. Vocab session done. We have learned what solute and solvent are. All right. So moving on then. We can also quantify the amount of solute in a solution. This is, we can kind of just condense this as one word, which is the concentration. So how concentrated your solution is a measure of how much solute is dissolved in it. And so we're going to see there's a couple of ways that we talk about this. The most common that we deal with in chemistry is something called molarity, or also known as molar concentration. But no one says molar concentration, everybody says molarity. And that is going to be the moles of solute, whatever solute you're looking at, per liters of solution. This is a very common way of doing that. And we use the unit of capital M, which we would say is molar. And 1 molar equals 1 mole for 1 liter. I'll make that prettier. Molar. There we go. This is the most common unit that we use. And so we can do some calculations with it. So we can say, I don't know, let's take 100 grams of potassium chloride. Is dissolved in water to make 1 liter of solution. Oops. Actually, let's make it not 1 liter. Let's say we're making it 1.25 liters. fancy. What is the molarity of this solution? So if we want to just rewrite this again, molarity equals moles per liter. We have liters, but we do not have moles, but we can find moles, right? 100 grams. We can figure out the moles of KCl using its molar mass, which I'm going to look up because I'm too lazy to calculate it. It is 74.55. Doing this. Oh, the spam is back. How exciting. I'll have to tweak with the spam filter on this. As always, don't click that. Okay, so we end up getting that many moles of KCl. The molarity is the moles per liter. So we can go ahead and figure that out. 1.34 moles. 1.25 liters. Let's do the math. And we get that this solution is 1.07 molar KCl. And so this is kind of how you would answer that sort of question. So because molarity only looks at one solute at a time, it's important that we, if there's a mixture or something, that we want to make sure that we're clear which component we're talking about. So the molarity of this particular solution is 1.07, and that's of potassium chloride. All right, so if there was another salt in there, we would have a different molarity for that particular solute. So this molarity is just for KCl in this situation. All right, any questions on that one? Okie dokie. We can do another one. How much glucose in grams is present in... There, let's make this a little harder. Let's see, let's look up what's the molar concentration of glucose in honey. Let's see if we have an answer here. No one has the answer. We do have a molarity. I'm just Googling this just for the fun of it all. Okay, blah, 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 blah. Okay. So we're going to just assuming all the sugar is glucose. There's probably other fructose and sucrose in there. Who cares? We'll just pretend. All right. So with this, we're now asking for grams, but we have a volume and a molarity. We can use those to go between solution volume and moles, right? Remember 6.01 that's moles per liter, right? Moles of glucose per liter. And so we also have a volume here, right? So if you want, you can use molarity as an equation and say, okay, well, moles is therefore just molarity times the volume in liters. That's okay. Or you could just use this as a conversion factor. And that's how I'm going to be using it throughout the rest of the course. So just keep that in mind. So if we have 250 milliliters, well, we're going to need to get that into liters first, right? Because molarity is moles per liter, not milliliter. So if we're going to do that, we have our conversion factor, right, to go from liters to milliliters. So now we'll be in liters, and now we can use our molarity. That's going to tell us how many moles per liter. And then if we really wanted to do this because it's asking for mass, its molar mass is here. So let's just, let me indicate what these are. This was the molarity. And this is the molar mass of glucose. And so we can do this all in one kind of calculation. So let's do it. So 250 divided by 1,000 times 6.01 times 180.2. We end up getting 270 point, actually I think that's 3 siblings all we need, right? Yeah, 6.01. Okay. So 271 grams of glucose. Hooray! Sugar overload. Don't drink 250 milliliters of honey. What is that? That's like a little bit more than half a cup, I guess. So quite a lot of sugar is dissolved in there. So fun stuff. So you'll die of diabetes if you eat that much sugar at once, I'm sure. So cool. All right, any questions on that one? So isn't this lovely? It's really just unit conversions again. I told you this is an important skill to have, so I wasn't lying. All right, well, I think that's a good place to stop for today. So we'll continue on with tomorrow. We'll talk about mass percents and molality, another way of talking about concentration. And then we'll talk about some properties of solutions. We'll have a nice video for you guys. And yeah, so on Discord, I'll go ahead and post some options for the exam, our third exam. So we'll see what you guys want to do with it. I'm open, and so we'll be good. Alrighty. Any other questions? Alrighty, I guess I'll see you tomorrow then. Enjoy your Tuesday.